another exciting talk. So it's my pleasure to introduce Jon Zink. So he is a graduate student at UCLA, and he is going to give our first contributed talk, and he's going to talk about scaling K2 planet demographics with galactic archaeology. So thanks, Jon. Everybody, please remember to put questions in the Slack channel and take it away. Thanks.
Thanks for having me. Just to reiterate what Kaylin just said, my name is Jon Zink. I am a PhD student at UCLA, and I'm going to be talking about planet demographics with the K2 mission. So I'll start by just mentioning that this is not work done in a bubble. You know, there's a bunch of people working on this. I'm just one of many people. Most of them are located in the SoCal region, so I suspect there's a large fraction of them on this meeting right now. But just to highlight, Jesse Christensen at IPAC, Kevin Harder-Allman at IPAC as well, and me, we're kind of the leaders of this collaboration, but there's many great scientists helping us along the way. Okay, so let's get started. Let's remind ourselves the Kepler mission. The Kepler mission stared at one patch of the sky. It was about 0.25% of the entire possible sky we could stare at, and it looked at it for about 4 years. That was really great. It really opened up the entire field of exoplanet demographics with this transiting data that we now had. But what happened is eventually this satellite failed. The famed reaction wheels kind of malfunctioned. That then gave birth to what is now known as the K2 mission. So one of the beauties of the K2 mission is it looked at 18 unique campaigns across the galactic plane. And you can see that while Kepler was wonderful and it stared at one patch, K2 really has some unique features. It really looks at a lot of different areas of the galactic structure, and we can really start to understand more about like exoplanet demographics, not just in one patch of the galaxy, but across the galaxy as a whole. So just to reiterate that point a little more, we can look at this edge-on view of the galaxy. And so on the left-hand side, I'm showing the Kepler sample, the stellar sample as a function of like galactic structure. And the right-hand side, we have the K2 sample. And you can see that the Kepler sample is mostly contained within this thin disk, or this region where the stellar sample is alpha poor. The alpha elements are not very abundant in the stellar sample. One of the cool things about K2 is that it actually reaches into this thick disk region. And that allows us to probe these alpha-rich stars and really see, are these alpha abundances essential for planet formation or not? We have some early evidence that suggests it is, but now with this K2 sample, we can really start to test that hypothesis and see if that is true. A few other unique things about K2 that really allows it to expand on Kepler is that it probes a much larger range of parameter space. So Kepler was mostly focused on FGK dwarfs, but one of the beauties of K2 is that since it looks at so many different regions of the sky, it actually has a lot more M dwarfs in it, almost 8 times the number of M dwarfs that was in the original Kepler sample. And so overall, it just spans a larger range of stellar mass and also stellar metallicity. So this really allows us to probe these different features of stellar sample and kind of use that to be a proxy for understanding the mechanisms that allow planets to form. Okay, so we've talked about K2. K2 is great. It's going to expand exoplanet demographics. But how are we going to do these exoplanet demographics on this sample? And so we really need to do any type of occurrence rate and really understand what the underlying population is we have to have 4 key ingredients. And the first one we need is a stellar sample. What are the stars we're looking at? We have to understand, you know, where are we probing, what are the masses, what are the radiuses, metallicity, and so forth, to understand, you know, what's unique about this sample versus the Kepler sample. We also need a catalog of planets. So this may seem obvious. Yes, you need to know there are planets there. If you don't have any planets, it's really hard to do demographics work. Not impossible, but very, very difficult. And then finally, you need to understand something about that sample. What is the completeness or the false negative rate of that sample? And also, what is the false positive rate? How reliable is that sample? Because otherwise, if we don't understand these biases, we really don't understand what the underlying population is at all. Okay, so this is kind of our goal here, is to do much of what was done for Kepler, but for K2. So let's start with the first step in our list of ingredients. we need a stellar sample. So this is work done by Kevin Hartery-Allman in our group. And basically what he's done is he's taken this photometric data from K2 and he's trained that on a random forest classifier using LAMOST and Apogee data and SDSS, 2MASS and Gaia, whatever was available at the moment. And he trained that photometric data to back out some really key stellar features. So understanding what is the radius, mass, the effective temperature, surface gravity, metallicity of all of these stars we have in our sample with just a few photometric data points. And doing so, he was able to create a completely uniform sample of K2 stars. So I just highlight a few features up here. The sample contains about 200,000 targets. Majority of them are FGK dwarfs, but there's a huge number of M dwarfs. So we have 8 times the number of M dwarfs that we had in Kepler. So this is really going to expand our understanding of the demographics for M dwarfs. And that's a really great feature of K2. Okay, so in doing so, one of the interesting features that popped out just basically for free is there was already a bunch of known planets for the K2 sample. And so by just improving the stellar sample, what we also did is we improved the planet radius of all of these known planets. And something cool really just popped out almost automatically. And we saw is that we were able to recover the known radius gap around 2 Earth radiuses. So you can see on the right-hand side, plotting the previously known distribution of K2 planets. And then in blue is what it looked like once we updated all the radius measurements. And you can see this nice little gap pops out. And that lines up really nicely with the gap seen in the Kepler sample. So just to remind people, this gap seems to be some kind of gap caused by formation. So we think this divides the gaseous envelope planets from the rocky planets on the left of it. This is still the mechanism which is, causes this gap is still a little bit unknown, and there's a lot to be done here. And K2 is really going to help with that. One of the things that's really great about this almost rediscovery is that we're verifying that this gap is not some observational bias of Kepler, but this is a gap that we're seeing across the field seen in K2. So this is definitely some kind of formation issue. Okay, so we have a stellar sample, we need a catalog of planets, and this is where some of the work I did comes in. And I created this thing called EDI-Vetter, and basically it takes all these unique transit signals and it vets them, accounting for all the K2 systematics. It's really built on a lot of what was done with the Kepler RoboVetter, but it's really cool. It's a great program. And what we were able to do is we did this on a test sample on the C5, the Campaign 5 K2 mission. And what we were able to do is create a completely uniformly vetted sample of planets containing 75 planets. 7 of them are multi-planet systems and 8 were previously undetected. And we recovered over half of the known planets in the K2 C5 sample. You may be wondering, that seems kind of low, but you have to remember K2 has a lot of unique systematic issues. So this kind of recovery is, we're quite happy with this 51%, although it's not near 100, but we can account for that, and that's really important. Quick plug, I have now made this EDI-Vetter program pip installable, so if you need to vet your transit signals using TLS, check out the GitHub. It's really great, super user-friendly, so anyone interested, please check it out. Okay, so I mentioned we have a catalog, we have a stellar sample. Now we need to measure our false negatives and false positives. So we can do this by running injection tests now into the light curves, and we can see what we recover on the other side. You'll note here we're plotting the completeness, and you can see in red that Kepler is very, very complete. Our K2 sample is not nearly as complete, and like I said, we recovered about 50-ish% of the planets, and that is reflected in our completeness measurement here. We're only getting about 50% of what we put in. Likewise, we can invert the signals and test the reliability and look for systematics that trigger true planar recoveries. And we find that our sample is really, really pure. We're getting about a 94% reliability. So that means that 94% of our planets are real signals and not systematic issues. Okay. So now we've run through our recipe. We have all of our measures. Now the big thing is we just have to mix and bake and hope that it just doesn't turn into a giant disaster like this picture here. So I want to remind everyone a few things of our sample. So I'm going to do a comparative analysis of Kepler versus K2-C5. You can see they're on very, very different parts of the sky, truly independent samples here. Furthermore, you can see they probe very different parts of the galactic disk. Both of them are relatively alpha poor, but they do definitely probe different unique features. So let's talk about what we found when we compared these two samples. Oh, sorry, really quick, I wanted to mention that they also have a difference in metallicity. So the K2-C5 has a lower overall metallicity than the Kepler sample. Other than that, it seems like many of the other features line up pretty okay. There's some minor uniqueness there, but the big one is the metallicity. We can see there's a slight deficit of metallicity in the campaign 5 K2 sample versus Kepler. So when we ran our demographics analysis through and ran our forward modeling pipeline, what we found is that, voila, okay, so what is this? This is the posterior distribution for our K2 sample versus our Kepler sample. And we can see this really high peaky Kepler sample. This means we have a very, very low uncertainty in our measurement, is a little bit higher than this green one here. This green one is our K2-C5 occurrence value. So we're seeing a minor deficit in planet occurrence in K2-C5 when compared to a similar FGK sample of of Kepler. And that's really interesting because I noted that there was a deficit of metallicity. So it seems to indicate that that deficit in metallicity may be causing us to have a deficit in planet occurrence in this sample. But one other thing to note is that there's actually a lot of overlap between these two distributions. So what this could also indicate is that this is early evidence that the Kepler field may be rather representative of the local galaxy, and it might not be quite as unique as we may have thought it was. So this is good news for Kepler, but there's definitely more to be done here. And I wanted to announce that we've now officially completed processing all of our K2 campaigns. So we now have all of the campaigns, not just C5 done. And we found is we have 730 planets with about 200 new candidates detected using this pipeline. So there's a lot of great new K2 science that's going to be coming soon. So keep your eyes out for that. There's really a lot of great work to be done expanding the exoplanet demographics, including K2 into our models. And with that, I will leave up my conclusions. And I just want to note that I'm going to be on the postdoc market, or I currently am on the postdoc market. So if there's any opportunities, please let me know. And just a reminder, we looked at K2 demographics. We found there's a minor deficit in our C5 sample, and that seems to be caused by the deficit of metallicity in the stellar sample. So with that, I will leave and take any questions. Thank you.
Amazing. Thank you, John. I also have to say, I've seen you give a bunch of talks, but I laugh every time about EDI-Vetter. Astronomy has a lot of bad acronyms, and that is not one of them. Thank you so much. And you and Steph have set the bar really high for great and funny animations and graphics in your talks. So as a reminder, people please use the Ceres Slack channel for questions. I'll start off with one. And you kind of beat me to it on your penultimate slide. So you focused on C5 right now, and you said that there are other campaigns and they're ready. Do you have a plan for how to prioritize them? So C5 being in lower metallicity, do you plan to start with others that span wider range of metallicity, or are there other science goals?
Yeah, that's a great question. So the plan right now is we want to release all these data products so that people can start doing their own demographics work. One of my personal goals, I'm going to go back a few slides, is I really want to think about how we can use this K2 to use and the Galactic Archaeology to kind of leverage some kind of demographics. So if we can take some of this K2 sample and like divvy it up into this thick disk region versus thin disk region, that's kind of one of my goals. So I think that's going to be across multiple campaigns and not specific to one campaign. But yeah, that's something I'm definitely thinking about.
Yeah, that'd be really interesting. All right, some questions are coming in on the Slack channel. So Eric Momajek says, John, why is the metallicity distribution for the Kepler stars so narrow? Plus 0.08 minus 0.13. This seems unexpected, as the metallicity distribution for the stars in the solar vicinity is about 0.2 dex RMS distributed around solar. Is that distribution solely spectroscopically derived metallicities, or does it include photometric estimates?
Yeah, so it's a combination of both spectroscopically and photometric. And yeah, this was actually one of the unique results of the Kepler sample, is that we found that it was not, it was similar to the solar distribution, but not similar to the local neighborhood. So this is a unique finding. I believe Andrew Howard did a bunch of work on this, showing that this offset was real and not just some weird figment of photometric systematics. So yeah, this does seem to be real, though, that there is this centrally located solar distribution for the Kepler sample.
Yeah, that is interesting. Well, thank you. In the interest of time, let's call it there. I'll note for Steph and for John, there are questions that I didn't actually have a chance to get to in the Slack channel, and I've started putting little check mark icons next to the one